Welcome to the third video in which we're going to discuss scaling laws. The objective of this video is to discuss how differences between the macroscopic and the microscopic world can be explained. This question is also illustrated on the right-hand side. Ants, for example, can lift up to 20 times its body weight, while humans can only lift up to 1.5 or maybe even 2 times their body weight. So how can this difference be explained? And the reason for that is that physical quantities, for example, forces, scale different as a function of size. And to evaluate this, one can use scaling laws. And the scaling law basically expresses the variation of a physical quantity with the size of the given system or object. And while this is done, usually other quantities are kept constant. For us, this means that we usually keep intensive properties such as the density or viscosity constant, because usually those are size invariant. This can be illustrated with the following example. If you think of a control element full of liquid and you now scale this control element down, the density of this liquid does not change and neither does the viscosity. But some forces that act on this control element may change. We now want to take a closer look how the different physical quantities scale. For this, we first consider a cube with a side length L, the surface area A, and the volume V. And if we now scale down the problem by a factor of 10, which means that we reduce the length of the cube by a factor of 10, we can immediately see that the surface area is scaled down by a factor of 100 because the surface area is proportional to the length to the power of 2. And the volume scales down with a factor of 1000 because the volume is proportional to the length to the power of 3. So this means that surface forces which act on the surface of our control element also scale as L to the power of 2, and volume forces scale as the length to the power of 3. For other forces or physical quantities, scaling laws can be found in literature. But please keep in mind that those scaling laws depend on the choice of size invariant properties. An example is the potential energy, which scales as L to the power of 3 if we keep the height constant. But if we don't keep the height constant, but also scale the height, the potential energy would scale like the length to the power of 4. So if you work with scaling laws, you always have to consider which parameters you want to keep constant. And the fact that forces or physical quantities scale differently as a function of size has some implications for microfluidics. And I would like to discuss some of those consequences with you now. The first aspect is that capillary forces become highly relevant at small scales. And this will be discussed in detail in the lecture on surface effects. But on the right-hand side, you can already see what capillary force is. If you insert a small capillary inside a liquid, usually a column will form, so the meniscus here will rise up your capillary, and this is due to the capillary force. At some point during this process, there will be an equilibrium between the capillary force and the gravitational force. And as you can easily see, for a small capillary, this effect is larger than for a large capillary, and this is due to the fact that the gravitational force scales differently than the capillary force, and hence at small scales the capillary force becomes dominant. We already discussed the next effect extensively in the lecture on fluid dynamics. The reason why flow in microfluidic systems is typically laminar is simply that the viscous forces dominate the inertial forces at small length scales. This can easily be seen when looking at the Reynolds number. This is the Reynolds number, and if you now consider the properties of the fluid, namely the density and the dynamic viscosity as constant or size invariant, you can easily see that the Reynolds number scales like L to the power of 2, assuming that the velocity scales linearly as a function of the length. And one last consequence is that diffusion becomes highly relevant at small scales. And to explain this, we can again look at a dimensionless number. And this time we look at the Peclet number, which basically gives us the ratio of the advective transport rate and the diffusive transport rate. And this can be calculated using this formula. So the Peclet number is usually a characteristic length, a velocity, and a diffusion coefficient. And if you now assume that the diffusion coefficient remains constant, because just scaling down our problem does not change the diffusion constant of our material, we can easily see that the Peclet number also scales like L to the power of 2. The concept of scaling laws is quite useful if you need to describe or analyze the physics of a given system. And using those scaling laws, you can easily explain most differences between the macroscopic world and the microscopic world.